Hello my esteemed viewers. In this tutorial we discuss clearly how we can analyze the concurrent force systems that are in equilibrium. So we are going to do this with multiple number of problems which are of engineering interest. In many applications of mechanics, the sum of the forces acting on the body is zero and state of equilibrium exists. As this boat, you can see here, is slowly lifted by several cables which are mounted over here. The sum of the vertical component of cable forces is equal and opposite to the weight of the boat. The horizontal components of the cable forces are also balanced. The elements of this truss 1, 2, which is attached over here at this joint, which are conveniently taken to the joint above, transmit concentrated forces to the joints at both ends, and the joints ought to be in equilibrium in order to safely transfer the loads. Otherwise, there will be relative movements between the parts. The apparatus shown over here, some kind of a cranky shaped container or holder is designed to hold the car body in the equilibrium for a wide range of orientations and tilts during the vehicle production. A complex pulley system, something like this, are easily handled with a systematic equilibrium analysis. These are all only few examples of significance of equilibrium analysis. The heart of the matter is that all supported systems will be in equilibrium. And because any system which is supported will generate what is called as support reactions. Here the supports could be wires, the support could be ceiling, the support could be floor, the supports could be container, the support could be a simple wire which is hanging a weight, something like that. In this example, here two weights W1 and W2 are hung through the wire. The wire in turn is fixed to the ceiling, let us say, and the kinks are formed at different levels due to W1 and W2 for the simple reason that W1 is different and W2 is different. Earlier the wire was taut, it was horizontal, and since the loads are hung W1 and W2, maybe fan, maybe some kind of a big bulb or whatever, it's going to adjust to a shape which is being shown over here by forming some kind of kink, one here and one here. For all practical purposes, we call this as a joint and this as a joint. And the tensions that are developed in the wires in this direction for this particular wire and in this direction for this particular wire, of course this is the weight acting, will neutralize the tension that is developed in the wire, will neutralize the weight, and it will keep the entire configuration of the wire in equilibrium. In this case, a sphere is supported by a V-shaped planes. The weight is the active force and that itself is the resultant, because in the absence of this support there is only one force over here. For a one force system, that force itself is the resultant. Here the weight is the active force and the resultant, it is taken care or nullified by the reactions that are developed to this tangential supporting surface in a perpendicular fashion. Whenever, it is very important to notice that whenever spheres are involved, the reactions that are emanated or generated by the supporting surfaces will always be radial, and they can be just moved with the principle of transmissibility to the mass center of this particular sphere while we analyze the equilibrium condition of this particular sphere. the block on the inclined plane generate the reaction perpendicular to the plane, and this is the weight, and this is the horizontal component of the weight down the incline, and this is the vertical component of the weight weight along this particular direction, and weight is the force, and this weight is resolved along the incline and across the incline, and this force will tend to disturb this particular block by pushing this block down the incline, while this component will generate a vertical reaction vertical to the surface of the incline. But anyway, all together will keep this block under equilibrium for a particular inclination of this inclined plane. The spheres placed will stand in equilibrium for a particular arrangement or particular placement. The weights of the spheres, here and here and here, three weights form the active forces. Therefore, their resultant will be sum of the parallel forces, weight of this, and weight of this. Anyway, if they are not supported one above the other, they should have gone disturbed. Anyway, due to this supporting system, self-supporting system, there will be reactions developed. While this sphere will receive the reaction from the bottom of this particular sphere, and here and here. While as far as this sphere is concerned, it is receiving the reaction from the top sphere, and of course at the floor the reactions will be generated. Therefore, these blue lines are reactive forces and the black lines are the active forces. Black lines are the causes, or the active forces are the causes, and the reactive forces are the effects. Anyway, active forces and reactive forces in tantrum will keep the system in equilibrium. Here again, there are four spheres contained in a container, enclosed container, and for a particular position initially they will be in misalignment, and they will be in disturbance, and they will not be in equilibrium. After some orientation is reached, they will be in equilibrium. Here the active forces are the weights of all the four spheres, and the reactive forces, as far as this sphere is concerned, this one from the bottom sphere and from the wall. And as far as this sphere is concerned, the reaction from this wall and the reaction from this bottom cylinder and this bottom cylinder. And as far as this particular sphere is concerned, the reactive forces are this due to vertical wall and the floor, and reaction from the top sphere. And as far as like this, we can also guess the kind of reactions that is being experienced by this particular sphere. Anyway, in an equilibrium system, whether it is concurrent or non-concurrent, and we will discuss threadbare when we deal with non-concurrent force systems, whether it is concurrent or non-concurrent, one important point to be realized is the system will be supported and system will be experiencing kind of a reaction due to active forces. Here again, there are some spheres contained in a container. Container will provide some kind of a support as far as this ball and this ball and this ball is concerned, and these three balls provide a support for the top ball. Equilibrium means, so in essence, in summary, equilibrium means if a system is in equilibrium, there is no resultant in that particular system. Algebraic sum of horizontal components of all the forces should be equal to 0. And algebraic sum of vertical component of all the forces must also be equal to 0. Not even a jerk is experienced by the system in any direction, either in horizontal direction or in vertical direction. The system will be in a balanced state of affairs. So here equilibrium would mean a kind of a balance that is achieved by the system in which are acted by the active forces and the reactive forces, the resultant and the equilibriant. Fundamental equations used while analyzing concurrent force system that are in equilibrium are sigma fx equal to 0. That is, there is no jerk, even a disturbance in the horizontal direction, and there is no disturbance in vertical direction, sigma fx equal to 0, sigma fy equal to 0. These two equations are also called as fundamental equations of statics as far as concurrent force system is concerned. Using these two equations, what we can do is we can find two unknowns that can be solved at the time using these two equations at a time. Therefore, in a concurrent force system, that is in equilibrium, we have to press sigma fx equal to 0 and sigma fy equal to 0 to surface in order to find maybe internal forces or whatever. And anyway, there is no way for us to find whether resultant is there. Resultant is found, and we will not be finding the resultant. We will be finding some other forces which are naturally reactive forces, which will keep the system in equilibrium. And nature of the problems therefore would include to verify if the system is in equilibrium or not. That means if to verify whether sigma fx equal to 0 or sigma fy equal to 0. And the problem may include finding reactions at the contact surfaces, and the problem may be of the finding the magnitude of the weights to be added to bring the system to the equilibrium, or the problem may be poking to finding the maximum weight that could be hung from a ceiling, something like this. So examples are galore. The internal forces in a wire, we may end up in finding internal forces in a wire, in a rod, as the case may be. So we will go through systematically problems after problems. Of course, the problem selected for this tutorial happens to be simple in nature, and as we go along this particular concept, we will tackle all the problems drawn from real world experiences. 14th problem. Of course, in the previous tutorial we have solved 13 problems related to finding the resultant in a concurrent force system. Therefore, the problems are cumulatively numbered. And the first problem in equilibrium analysis of a concurrent force system is a sphere of weight 100 Newton and radius 60 millimeter is attached to a string of length 120 millimeter and fastened to a vertical wall as shown. Determine the force in the string and reaction from the wall. Of course, there is a ball which is being hung using this particular wire, and this wire must be nailed to this particular wall, and the length of the wire is 120 millimeters. And the radius of this ball is 60 millimeter. That means from here till here it is 60 millimeter, from here till here it is 120 millimeter. Of course, the dimensions given in a problem will help us to find out the angles with which the interior forces make. Okay, and the tension is the internal force. Of course, a wire, as said earlier, a wire can experience tension only, which is shown by an arrow away from the joint, and here is the point of concern. And we will write the free body diagram of the center of mass of this particular sphere. And this sphere will also experience, this is the weight of the sphere, and this sphere will also experience a reaction from the wall. And we will just disassociate the entire figure, and we will be centric on writing the forces only, because that is good enough. That is the concept of free body diagram, which has been told maybe in the second tutorial. And this we will name this particular reaction as RWS, reaction from the wall towards the sphere. And here it is. This is the tension in the wire, and this is the weight, and this is the reaction from the wall. And this angle can be computed by making use of the geometry of this particular arrangement. And if we take sine theta, we will know the opposite side and the hypotenuse. Therefore, we can calculate sine theta equal to 60 by 120. Therefore, theta happens to be 30 degree. So we will religiously write this. This is tension in the wire, and this is 30 degree. This is the reaction from the wall, and this forms the free body diagram of this particular sphere. And we will take it to the next slide, so that for the sake of clarity. And this is the free body diagram of the sphere, and we will put sigma fx equal to 0. I think we are supposed to write over here the algebraic sum of horizontal components of the forces should be equal to 0. So RWS positive going towards right, minus t sine 30. The horizontal component of t is acting in this direction leftwards, and it is sine 30 because the angle is referred with respect to vertical. So RWS minus t sine 30 equal to 0. Therefore we will get a relationship between RWS and 0.5t, but still two unknowns remain. We will press the other equation into service, that is sigma Fy equal to 0. We will get to develop an equation like t cos 30, which is acting vertically up, the component of this particular tension, which is up, which is going like this. Therefore it is positive, minus 100 equal to 0. Therefore we will send that 100 that side. Therefore we will get to know what t is. It is 100 by cos 30, that is 115.5 Newton. We will substitute this back over here and we will get RWS, that is reaction from the wall, to be 57.75 Newton. And the 15th problem goes like this. In the figure, W equal to 80, P equal to 10 Newton and D equal to 200 millimeter. Determine the value of the H consistent with the equilibrium. Of course, this problem needs some kind of a pre-processing. Before applying this particular weight, consuming this particular sphere, this wire was turned and it was horizontal. Now, after placing the sphere of weight P, that is 10 Newton, this wire naturally should sag. It will sag like this to a particular depth H, and it will attain its equilibrium in this particular position. In order to disturb this, either we have to remove this weight or we have to increase this particular weight. The question is, find the depth of depression. How deep this will go sagging down and it will adjust. Okay, that is the question. Therefore, we will just find it out by the principles of equilibrium analysis. Here, in order to determine the tension in this particular wire, so without finding this, we will be struggling over here, because this is an unknown. The tension in this wire is unknown. Tension in this wire is unknown. There will be three unknowns. Three unknowns cannot be solved in a concurrent force system because we have only two equations that are discrete. Therefore, we will make a cut over here, and we will analyze the equilibrium of this particular weight. This is also in equilibrium. Therefore, the free body diagram of this weight happens to be like this. There is a tension going up in this wire, and there is a weight of this. Weight is 80 Newton. Therefore, tension, and if you apply sigma Fy equal to 0, T equal to W. That is the equation. Therefore, T equal to 80 Newton. Then we know now what is the tension in this particular wire. We will just translate this. This is 80 Newton. This is tension, we don't know, and this is 10 Newton, and this is the inclination theta. Once we find this inclination theta, it is very easy for us to find out what is the dip of this particular wire when the weight of 10 Newton is added. Before it was straight. Of course, we will apply sigma Fx equal to 0. It becomes 80 cos theta positive equal to T cos theta. 80 cos theta equal to T cos theta. Therefore, T equal to 80 Newton. 80 Newton. Of course, we could have straightforwardly written, but anyway, this problem will help us to understand a wire cannot experience different tension values. Sigma Fy equal to 0 we will apply, and we will have, and the system is symmetrical. The system is symmetrical, same theta over here and over here, same tension. Therefore, sigma Fy equal to 0 would only amount to T sine theta plus 80 sine theta. T is 80 sine theta, 80 sine theta. 2 times 80 sine theta equal to 10, which is going vertically down. Therefore, we will get theta equal to sine inverse of 10 over 160. 10 over 160. And we will get 3.58 degree. This angle is 3.58 degree. So with the help of this angle, we can find out from the figure tan 3.58. We will go back to this figure. This angle is 3.58, and this height is, we don't know, but this distance we know. Distance is 200 millimeter. Therefore, tan theta equal to opposite by adjacent. Opposite is H, the unknown. The adjacent is 200 millimeter. Therefore, we will get to know the height of depression, how deep the wire comes down. It is equal to 12.5 millimeter. Determine the forces that the members exert on joint B. On joint C should have been C. Yeah, joint C in this particular arrangement. So there is a joint C over here. This joint C is being pulled in the rightward direction by 2000 Newton for some reason. It's an active force, and there is a weight that is being hung which is equal to 1000 Newton. The question is, what is the forces in the member CA and CB? Initially, it's really tricky to guess whether CA is in tension and CB is in compression, or CB is in tension or CA is in compression, or both of them in tension or both of them in compression. So in such cases, that means in a joint, if we find 2 or 3 members with unknown forces, it's better we assume them to be under tension. Therefore, with that particular pretext, with that particular assumption, we have just drawn the internal forces in CA to be tension, TCA, and the internal forces in CB is to be TCB, that is also assumed to be tension. It makes an angle of 45 degree, which is given with respect to vertical, and this makes an angle of 30 degree with respect to vertical, and these two red forces are active forces. It's enough if we analyze the equilibrium, and the system is in equilibrium under the action of active forces, 2 active forces and 2 reactive forces. And we will apply sigma fx equal to 0. We will get TCA sine 30 negative minus TCA sine 30 minus TCB sine 45 plus 2000 equal to 0. We would have written. Anyway, if you send 2000 that side, it will also become negative. The entire equation becomes negative. Therefore, they would cancel away, leading this particular kind of an equation. Had we precisely written, we would have written minus TCA sine 30 minus TCB sine 45 plus 2000 equal to 0. So therefore it has been adjusted, modified, tweaked, and we will get 0.5 TCA equal to 2000 minus 0.707 TCB, a relationship between TCA and TCB. Still, the problem is not solved because we are still with 2 unknowns, TCA and TCB. We will continue with the problem, and here is the relationship, and we will apply sigma Fy equal to 0 to the same free body diagram, and we will get TCA cos 30 going vertically up, positive, TCB cos 45, TCB cos 45 going vertically up, minus 1000 equal to 0. So 1000 is sent to that side, RHS, so it becomes positive 1000. Therefore, and we will apply that particular relation over here where in the place of TCA, and we will get this equation, reduced equation, and finally we will come out with TCB to be 4741.9 Newton, and it has come out to be positive. Therefore, as far as TCB is concerned, it is under tension and our assumption is correct. And we will substitute the value of TCB in equation number 1. That is over here. We will get to know what TCA is, and TCA emerges out to be negative minus 2705. Therefore, we will just remove this TCA over here, and we will replace this by reversing that particular force, and it should be like this. So negative sign indicates that our assumption of TCA of being in tension is wrong. It is in compression. Therefore, the sense of the force needs to be reversed. Of course, it should be reversed and it should be written like this. Therefore, member CA suffers compression as an internal force, while member CB suffers from tension. But anyway, their sufferings will keep the system in equilibrium. A portable bin, that is a bin weighing 1000 Newton, determine the chain length ACB. It's a sling chain which has been adjusted uniformly. AC equal to AB. AB cannot be longer than AC or nor vice versa. if AB is longer than AC, it will be tilting towards the right. On the other hand, if AC is longer than AB, it will be tilting to the leftwards. Therefore, it is adjusted in a symmetrical position. But anyway, we need to find out the length of CAB, the length of this particular wire, given the dimension of the box, given the weight. And it is being hung by attaching to a hook. The hook is tied to somewhere to the ceiling, and here is the hook. Therefore, this particular wire should receive all the weight, the entire weight, in the form of tension. And this tension and the tension in the chain should not exceed 1300 Newton. If it exceeds, it may end up in breaking. Therefore, the possible force, the maximum amount of force that can be developed in AB and AC, the entire chain should be limited to 1300 Newton. Therefore, we will write the free body diagram of this. The box becomes immaterial because we are concerned with this equilibrium of this particular joint. So this is the free body diagram of joint A, and here is the weight which is going up, which is being resisted in the form of tension by this particular wire. This is 1000 Newton, and the tension here, it makes an angle of theta, and tension here is limited to 1300 Newton. So 1300 Newton, 1300 Newton as an internal force with a limitation. Okay, and that means the internal force that can be possibly developed is given. We will take that way. Therefore, theta becomes unknown. We will just write sigma Fy equal to 0 because this joint is in equilibrium. There is no tilt either to the right or to the left. Therefore, sigma Fy equal to 0. 2 into, because it is a symmetrical system, 130 cos theta plus 1300 cos theta equal to 1000. That's how we have written, would have written. Therefore, it is 2 times 1300 and 1300 cos theta equal to 1000. Therefore, cos theta equal to 0.384. The force system is telling us what should be this angle. So theta happens to be 67.7. Therefore, angle subtended by these two wires happens to be 2 times 67.7. So therefore, we get to know the geometry. It becomes 135.7. Therefore, these two angles can be calculated from the principles of triangle. So ACB or ABC must be equal to 180 total internal angle minus 135.7 consumed by this particular angle divided by 2. So it becomes 22.3. Since this length and this length are equal, the opposite angles will also be equal. It becomes equilateral triangle. And this 360 millimeter is given to us. Therefore, we can find out what should be the length of this by making use of cos theta. So cos 22.3 is adjacent by hypotenuse. Adjacent is half of 360. If you consider this half of the triangle, it is 180. This is 180. 360 by 2. 180 by L. Cos 22.3 is adjacent by hypotenuse. Adjacent is 180, hypotenuse is L, and we will get L to be 194.55. That is, half length of the chain is 194.55. Therefore, total length of the chain should be 194.55 into 2, that is 390 millimeter. So therefore, 390 millimeter sling of the chain can keep the system, keep the box in equilibrium, not allowing it to tilt either rightwards or leftwards. So 18th problem is determine the forces in the members AC and AB shown in figure due to the action of the horizontal force applied at C. So this resembles maybe our third question. Anyway, it's a different try. Of course, there are two bars which are being adjusted like this. There is a horizontal force applied. And this comes with the geometry, height being equal to 2.5 meter, and this length is 3 meter, and this length is 2 meter. So with the given dimensions, we can calculate what theta 1 is, and that is theta 1 equal to tan inverse of opposite by adjacent. opposite is 3, adjacent is 2.5. Therefore, this angle happens to be 50.19. On the other hand, theta 2 becomes tan inverse of 2, opposite by adjacent, that is 2.5. It becomes 38.65. Therefore, we will take out this particular joint and analyze for its equilibrium. So therefore, free body diagram, here again we don't know which is compression and which is tension. Therefore, for time being, we will presume that both the members are showing an internal reaction of or internal force of tension only, and we call this as FCA going away from the joint, and this is FCB going away from this joint. Of course, this is the given force, and we will take it to the next slide for the sake of clarity, and we will apply sigma Fy equal to 0, algebraic sum of vertical forces equal to 0. Therefore, we will get minus FCB cos 38.65 going down, minus FCA is also going down, cos 50.19 equal to 0, because there are no other vertical forces given. Therefore, we will establish a relationship between FCB and FCA. FCB happens to be minus 0.9 FCA. We will apply Fx. Still we have not solved. Therefore, we will apply the other equation that is available to us, that is sigma Fx equal to 0. So upon applying this, FCB sine 38.65 going in the rightward direction minus FCA sine 50.19 going in leftward direction plus 1000. The given force must be equal to 0. Therefore, upon solving this, we will find, and we will replace this FCB by minus 0.9 FCA. Therefore, we will get to know that FCA is 751 Newton and it is positive. Therefore, our assumed dimension as far as FCA is concerned is correct. It is suffering from tension as the internal force. And we will apply known value of FCA to this equation, and we will get to know as to what FCB is, and FCB emerges to be negative. Therefore, our assumed direction is wrong. Therefore, we will just reverse this force because it is suffering from compression, and this assumed direction is incorrect, because we have assumed that it is away from the joint. Away from the joint is always connote tension. So therefore, it should be replaced by a force FCB in this direction, acting at this particular joint. Right. The 19th question is, find the tension in the wire AB of length 160 millimeter that ties two cylinders of weight 100 Newton. This is 100 Newton, this is 100 Newton, and diameter 120 millimeter each. All of them have 120 millimeter diameter. Those two cylinders support another cylinder of diameter 120 millimeter and weight 200 Newton. If this is 200 Newton, these two are 100 Newton. And the question is, what is the tension? Definitely, in the absence of this particular wire, this sphere would have rolled to the left and this sphere would have rolled to the right. If they are held in tandem, that means this particular wire is supporting these two spheres, sustaining itself a state of tension. So, and this is the reaction offered by the floor to this sphere and this sphere. By virtue of the symmetry, this reaction should be equal to this reaction, and this is the reaction offered by the top sphere to this bottom sphere, and this is the reaction offered to the top sphere by the bottom sphere, and this is the tension experienced by the wire. The internal forces are written, reactive forces are written. So we will take away, we will analyze the top sphere first, and we will get to know this particular reaction, and we will just reverse that, and we will analyze any one of the spheres, and we will get to know the unknowns, because this sphere need not be solved because of symmetry. Tension we will get over here. This reaction we will get by analyzing A. So we need to analyze only C and A. So accordingly, so this is the triangle that is being formed over here. This length is 160 millimeter and this is 120 millimeter. 60 this radius and 60 this radius, and the reactions we should always remember, whenever spheres are involved, the touching surfaces of the spheres will experience reactions in a radial direction. Therefore, this is 120 millimeter, 160 millimeter. Therefore sin theta over here is opposite, that is 80 here till here, and hypotenuse 80 by 120. Therefore theta becomes 41.75. Therefore this total angle is 41.75 into 2. So we will take up the top sphere, FBD of the C, that is the top sphere. This is the reaction offered by the bottom sphere to C. Therefore we will call it as FAC. FAC, reaction offered by A towards C, and this is the load, this is the weight of C, and this angle is 75, and by symmetry FAC equal to FBC. Therefore you need to find only FAC. If you apply sigma Fy equal to 0, we could say 2 times FAC cos 45 equal to 200. It has been of course written loosely. Anyway, we can say that. So 2 times FAC cos 41.5 equal to 200. Upon simplification, we will get 1.5 FAC equal to 200. Therefore, FAC equal to 133.33. So one of the unknowns is solved. Now, this is the reaction offered by the top sphere to the bottom sphere. We can call it, you could have called it as FCA. But anyway, we know the value, therefore we have replaced this value. This angle we have already identified to be 48.25, because 41.75 plus 41.75, okay, 180 minus 2 times 41.75 is the angle that is left over here by 2. That will get us 48.75 in that particular triangle. Okay. So this is 2 times 41.75. This angle is 180 minus 2 times 41.75 by 2. That amounts to 48 point something that we have written over here. Okay. So this is the free body diagram. There is a reaction from the floor. This is the tension in that wire that is being asked. And this is the pressing that is being done by the top sphere to the bottom sphere, and this is the self weight of E. So sigma Fy equal to 0. Anyway, here remains only 2 unknowns, RF as well as T. We can easily solve it. First of all, we will apply sigma Fy equal to 0, which will give us RF going vertically up positive minus 133.33 sine 48.25, which is going down, coming down, the component of this force, minus 100 the weight. So RF we will get to be 200 Newton, and if you apply sigma Fx equal to 0, T, which is positive, minus 133.33 cos 48.25, which is making the ball to move that way, okay, equal to 0. Therefore T happens to be 88.8. So we have found tension in that wire and also the reaction from the floor. So the last question is, a solid sphere of weight 1000 Newton rests on 2 parallel cylindrical rods. This is a rod and this is a rod. Here there is a big sphere of 1000 Newton. They are in the same horizontal plane. That means if you can draw a line which will just be tangential to B and C horizontally. They are on a horizontal plane. Therefore, they will receive a vertical reaction. Okay. The distance between the bars, that means distance between these bars, center to center distance, is equal to the radius of the sphere. So if the radius of the sphere is r, this distance is also r. That is a clue given to us. And here is a weight acting, and this is the reaction that is shown by this sphere towards the big sphere, and this is also the reaction shown by this sphere towards the big sphere. And of course the symmetry will tell us that this reaction should be equal to this reaction. Anyway, we'll write this RBA, the reaction offered by sphere B towards A, reaction offered by C towards A. And this angle is 30 degree because this forms an equilateral triangle R, R and R. In an equilateral triangle, angles are 60 degree, and here we have written a vertical for the sake of ease, for the sake of clarity, because we need to resolve sigma Fy, sigma Fx equal to 0. So this is 30 degree, this is 30 degree. And sigma Fy equal to 0 will lend us to say this, RCA cos 30 going up plus RBA cos 30 going up should be equal to 1000, which is coming down. If you send that side, it will become 1000. So 2 times RCA, because RCA equal to RBA, cos 30 equal to 1000. Therefore RCA equal to RBA equal to 2 times cos 30, 1000 divided by 2 times cos 30, which happens to be 577.4. With this, we have completed the tutorial number 4, which dealt with simple problems related to equilibrium of concurrent forces. Therefore, in essence, this tutorial we brought out solutions to some typical problems related to equilibrium of concurrent force systems. In the next tutorial, we shall go through still problems related to of this kind only, that is related to concurrent force system, of course with a little increased complexity and related to real world or the problems of real world or engineering concern. Until then, bye and thank you. If you have liked this video, please subscribe.